The biggest challenge facing orbital computing may not be physics. It may be economics. Once the theoretical architecture is examined, the scale becomes difficult to ignore. The relevant number is not the weight of the processor or GPU. It is the complete spacecraft, computers, solar arrays, radiators, batteries, structure, propulsion, shielding, communications, cooling systems, and disposal capability. Suppose, extraordinarily optimistically, that each complete computing spacecraft weighs only 1 ton. A fleet of 1 million spacecraft would therefore require 1 million tons of hardware delivered into orbit. Even at a future launch cost of just $100 per kilogram, transportation alone would cost around $100 billion. At $500 per kilogram, the figure becomes $500 billion. At $1,000 per kilogram, it reaches $1 trillion, and that is only the initial deployment. Spacecraft do not last forever. If a million spacecraft fleet has an average 5-year life, approximately 200,000 spacecraft would need to be replaced every year simply to maintain the constellation. At 1 ton each, that represents 200,000 tons of replacement hardware annually. This creates a permanent logistics treadmill. Cheaper rockets help, but they do not make the mass disappear. The same problem appears in launch cadence. If a launcher could deliver 100 tons of useful computing infrastructure per flight, deploying 1 million tons would require around 10,000 launches. Maintaining the fleet could require thousands more launches every year. Then reliability becomes a mathematical problem. At enormous launch volumes, even very small failure probabilities eventually produce recurring losses, and launch failures are not necessarily independent. A common engine, software, manufacturing, or thermal problem could potentially affect an entire fleet and interrupt the replacement pipeline. There is also an environmental dimension. A constellation containing hundreds of thousands or millions of spacecraft eventually creates enormous numbers of objects that must be managed, deorbited, and replaced. Manufacturing, launching, operating, collision avoidance, and reentry all become part of the life cycle equation. This leads to the central investment question. Is orbital computing merely possible, or can it produce useful computation more cheaply than computing on Earth? That is the standard that matters. A spectacular vision can justify experimentation. It can justify research. It can even justify enormous investment. But at terawatt scale, the burden of proof changes. Power density must improve. Spacecraft must become lighter. Lifetimes must increase. Launch costs must fall dramatically. Manufacturing must become almost unimaginable in scale. Reliability must approach industrial levels. And the complete system must ultimately deliver computation at a competitive lifetime cost. The dream is not necessarily impossible, but the numbers demonstrate that the real competitor is not physics. It is economics.